Welcome class to Chapter 1. In Chapter 1, we're going to look at the basics of GIS data. We have to start somewhere, so we're going to look into the complexity and the variety of GIS data in this chapter. So one thing I want to talk about is what a data model is. Basically, a data model, it has laws and rules that describe the real-world features in a computer, basically. So if you see on the right, we have the real world, and then if we take that real world and flatten it, we have a map. Now, and we're going to talk more about this later, the two basic kinds of GIS data include raster, which is this one right here, and vector data. And we'll get into more about how these data models work. Let's take a step back and talk about what geospatial data is. Geospatial data basically is any kind of data that has a location in the real world. Now, in GIS, we mostly have spatial data, but sometimes we have aspatial data, or in this case, non-spatial data, which is data that doesn't really have location information in it, such as data in a table, which we'll talk more about in this chapter and in Chapter 6. So I like to think of all the geographic data that we are going to deal with has three components: geospatial, which we just talked about, attribute, which we'll talk about later. These are the data in tables, and they may be non-spatial. And we also have something called meta, which is metadata. In GIS 33, you're going to learn a lot more about metadata, but we're going to talk a little bit about that in this chapter. So spatial data, just take a step back again and not talk about the data models in GIS, but just spatial data in general. Spatial data can be classified as either discrete features, which in this case we have house addresses, transportation, and parcels, or continuous data, where there's always a value anywhere across the earth, like elevation, except maybe over the oceans. Well, over the oceans would have a zero, would have a zero value. You could have a satellite image which has pixels at every location that is covered by its spatial extent. And then we have attribute data, which I've talked about already. And this is something that's very powerful about GIS. Data in GIS don't just have a spatial component, but they also have data in tables. So we can put a lot more information in these tables that could add complexity and power to GIS. And then we have the metadata. Metadata is just simply data about data. Oftentimes when we create a data set, we need to add information about the data set. Where did it come from? What is its purpose? Is it public or private? Are there use limitations? What is the spatial accuracy? What is the vertical elevation accuracy, etc., etc.? So it's not always sufficient just to have the data in GIS. You very much need metadata as well. Date also is a very important piece of metadata. Okay, so let's go back to our two basic data models, again, which is raster and vector. Let's start with raster. So in a raster data model, as you see here on the left-hand side, is basically a representation using pixels. Now, an entity I've described here down here on the right, and it basically is just any geographic feature that is going to be modeled in GIS. You can think of a model as something that is an abstract, or it can be a simplified representation of an actual geographic, or I should just say an actual feature on the Earth's surface. So we are comparing raster view of the world, which are all in pixels, to vector. And if you're doing, for example, vector entities of houses, you would have points. For lines like ski lifts, you would have literally a line. And for areas, you would have a polygon. But these are a little bit different when they are used in the raster model. They kind of look like lines, they kind of down here look like polygons, but again, they're all based on pixels. So raster data, again, uses pixels and something called a cell-by-cell encoding. Basically, each pixel or cell, we use cell in GIS, has a value. And in this case, what we're looking at here is 1 representing residential areas, 2 representing forest, and 3 representing farmland. And we can divide that up into this grid to be represented by a raster data structure. Now, continuous data are best represented by raster data because there's always a value no matter where you are in this raster data set. Some examples of continuous data, again, would be elevation, temperature, soil pH, etc. So displaying rasters, even though continuous data are best represented by rasters, it does not mean that rasters only use continuous data. We can also represent discrete features using rasters. And they usually represent lines and objects on, let's say, a topographic map. And continuous data, though, on the other hand, will have data in every single cell or pixel within the spatial extent. Here's an example of a discrete raster. So what we are doing is we're using raster cells to represent very individual discrete features, such as what looks like, it could be a road, I'm not quite sure, but definitely this is a lake. We have contour lines that represent elevation. This is very typical for a discrete raster. This is elevation, and we're looking at elevation from low values being in the bluer range and redder values being high elevation. There is an elevation value for each pixel here. So again, this would be an example of a continuous data set. So some advantages of raster models. Very simple. It's uniform in size and shape. It's cheap. Disadvantage. They're very large data sets. If you are trying to represent discrete data, it doesn't look as good. You don't have multiple attributes, so you don't have that power of the attribute table. And different scales could be really hard to deal with. If you're zoomed out, you might be okay, but if you zoom in on a raster data set, you start to see the cells. It's like zooming in on your TV and you start to see pixels. It's not going to be that great. So just like anything, there are pros and cons. So this brings us to vector spatial data. Vector data, instead of using cells, we use discrete features. We use actual geometric objects like points, lines, and polygons to represent features on the Earth. So let's start with points. A point is basically a 0 dimension. It has a location, x, y. We'll talk about in Chapter 3 the coordinate systems. And there's a lot of different features that are represented by a point. I just have some examples here, like a post box, a tree, a lamppost, a house, if you zoomed out, even a city. So points are very clean, very nice, and very neat. And again, with vector data, we have tables, multiple attributes assigned to each feature, and therefore is very powerful. We can have lines, which are one dimension. Some examples include roads, power lines, rivers, county boundaries, state boundaries, freeways, etc., etc. And they consist of nodes, basically right here, nodes and vertices that are connected by lines. And then of course we have our polygons, which show area. Polygon is two dimensions and has properties of location of the vertices, has an area and perimeter. Examples would be, like I wrote here, a field. If we're zoomed in really tight there, we can do buildings. If you zoomed out, buildings would be a point. Lakes, we could have states, counties, cities if we're zoomed in. And all sorts of things. So within a GIS data display, we could have points, lines, and polygons all being plotted at the same time. They will probably be different feature classes or shapefiles, which we'll talk about later, but they are pretty powerful for discrete features. Now, I mentioned a couple of times zooming in and zooming out. So I want to talk about large scale versus small scale because some students have a hard time understanding or remembering the difference. So when we're dealing with small scale, we're dealing with areas that are zoomed out. So in this map, this is a small scale map. A small scale map would have rivers being represented by lines and cities being represented by points. You can think of small scale, little detail. On the other hand, if we're zoomed in a lot, then we have large scale, a lot of detail. And instead of rivers being represented by lines, in this case, rivers are actually being represented by polygons, just because we're zoomed in enough to be able to do that. Now, when we change the resolution of rasters, the look of those rasters changed as well. So for example here, we have a 5x5 grid that represents a street network. And if we add more and more pixels, that street network gets more and more detail. We could do the same with vector representations of it as well. The more vertices that we have, or points, the more detailed it is. But what's interesting is that vector data don't necessarily lose its look that much when we change scale as much as raster data does. So advantages of vector, we kind of saw it already. Good representation of reality because there are a lot of discrete features out there. It's compact, we can use topology, we'll talk about that later, and the graphics, the visual representations look good. Disadvantage, they are not good for representing continuous data. You would not want to use a let's say you're representing temperature across Los Angeles. You do not want to use vector to do that. Now a tin, which I have right here, is one way to address this issue when it comes to elevation. Elevation is a continuous data, but a tin can help with that. Some other disadvantages. Spatial analysis, which we'll get into a little bit in this class, maybe more in future classes. It's very difficult to do with vector data. Raster data are better for spatial analysis, and some of the analysis that you use for vector could be quite time-consuming. Another advantage, and I shouldn't say another, this was part of the last slide, a little bit better handling of topology is one big advantage of vector data. What is topology? Again, topology is something you will look into a lot more in GIS 33. Essentially, there are a set of rules on how things are spatially related. So we see here on the left, this is topological, and there are labels for each segment and labels for each point, and even labels for each polygon. And those labels contain rules. You can have one that's basically very tight and neat, or you can even have warped topological data and rules. Alright, so the very basic form of topology is an arc, which is a line that represents basically a set of 2 points. A node is the beginning or end of an arc, and arcs and nodes can start to form topology. For example, if you look at arc ID A goes from point 1 to point 2, which makes sense, right? From 1 to 2. And then arc ID B goes from 2 to 3. And this is topology is important not just to maintain the integrity of the geometry of vector data, but it can also be used for networking like road networks. For example, let's say A and B are one-way streets. Then we know that they have a directional component from and to. Some other rules of topology that really get into the integrity of your geometry. There cannot be any gaps or overlaps. There should not be any duplicate copies of anything. No nodes should exist where there are less than 3 lines intersecting. No overshoots, no undershoots. So when you're digitizing, which is again something you'll learn in GIS 33, you cannot have an undershoot or an overshoot. And all arcs are connected by nodes. And these topological rules are very important when we get into either coverages, which is a type of data set in ArcGIS, or geodatabases. Now, in addition to raster and vector data, well, actually these are raster and vector data, I want to talk a little bit about other kinds of data models. A surface model is basically a representation of a continuous data set that's on the Earth's surface. Elevation is the most common surface model. We could have a digital terrain model, which is basically a grid of height values, and you can create hill shades or slope from those things. You could also create a tin. I mentioned a tin earlier, and a tin, unlike what we just saw, which was raster, a tin is actually vector, and we use small triangles to represent the terrain, and peaks and depressions are also embedded into this sort of wireframe triangular model to help shape or basically represent the shape of the topography of Earth. And what's interesting is you can actually drape on top of this tin satellite images, you can drape buildings, and other kinds of vector and raster data. You will learn later on in GIS that the tin is best represented in a 3D representation of Earth, and that's often done in a program called ArcScene. Okay, so let's talk about some fundamental data set types. We broadly talked about 2 data models, vector and raster. We talked about geographic data having either discrete features or continuous features. Now, more specific data types that we find in ArcGIS is what we're going to talk about now. So what you're seeing here is we have tables, we have feature classes, which are basically vector data, and we have raster data sets, which mostly could represent continuous data, but it could also represent discrete data. In ArcGIS, and in this class, we are going to be using mostly shapefiles and geodatabases. Coverages is an older format of ArcInfo, and sometimes you might run into these in the real world, but we aren't going to be using them that much. Database connections, we'll look into that later on. We will be creating layer files and rasters and standalone tables. So unlike shapefiles and geodatabases that have tables attached to them, you could have standalone tables that aren't really associated with a spatial data set. We will use a few internet servers here and there. I don't know how much work we're going to deal with when it comes to TINs, at least not in this class. And we can't forget about CAD, Computer Automated Drafting. Sometimes architects, engineering, they will have CAD drawings, and you have to import those CAD drawings into ArcGIS. We will not be doing that in this course, but in the real world, you may have to deal with CAD drawings. So let's talk for a second about coverages. Coverages, again, is the older model, and what's nice about coverages, though, still, is that you can have more than one type of geometry. For example, in this coverage of streams, we have annotation, we have arcs, which are basically lines, and we have ticks, which are basically points. And we can also have topology, topographical rules. Sometimes a coverage is called a georelational data model. Yeah, this is an important tip too. Do not use Windows to copy or delete basically any kind of GIS data, especially coverages, shapefiles, and geodatabases, because there's all these multiple files when it comes to this. We want to use our catalog, and in Chapter 2 we'll talk about how to use our catalog in managing GIS data. One other thing, avoid spaces when it comes to names of GIS data and folder names. Then we have a shapefile, which is also georelational, but there's no topology with the shapefile. Notice here that a building's shapefile in Windows Explorer would have all these files associated with that. But if you look at these shapefiles in our catalog, which is kind of like Windows Explorer, but more specific to ArcGIS, it's just one. So if you're copying or deleting, it's much more efficient and safe to use our catalog. Again, and this is important right now, but these are what the individual files represent when we're looking at them in Windows Explorer. Then we have the GeoDatabase. Now the GeoDatabase is the object-oriented data model and is the latest and greatest way to represent data in ArcGIS. And we can break down a GeoDatabase into its featured data sets, which have multiple data in them, or feature classes, which is basically only one type of geometry. So within a featured data set, we can have multiple types of geometry, unlike a shapefile. Kind of like a coverage though, but unlike a shapefile. And there is they usually are used to organize a bunch of GIS data for an area. And then we have our feature classes, which is like a shapefile, and it contains similar features grouped in that set. And basically, again, only one geometry is allowed. We will talk about geodatabases more associated with Chapter 2, and then in GIS 33 we're going to get into a lot more about them. So here are a couple of different types of geodatabases. You can have a single user geodatabase, which isn't very common. A personal geodatabase, I'm doing this one last because this is the next one that came out. It's pretty limited. You usually only have, I think, like 2 gigabytes of space, and it's based off of an older version of ArcObjects. And then we have a file geodatabase, which is nice because it has much larger space. And if you actually use Windows Explorer, all the files that are associated with File GeoDatabase are in one folder. So you can actually use either Windows Explorer or ArcCatalog. Now later on, you might deal with multi-user geodatabases, which again is the most common. And this is really important when you're dealing with multiple users in the workplace. Okay, just a couple other things I want to talk about. We're going to look into ArcMap. ArcMap is basically the mapping feature of ArcGIS. We're going to start with using GIS data in Chapter 1 and playing around with ArcMap. So what I have here is basically just some names of some of the characteristics that you will see in ArcMap. ArcMap is a Windows-based software, so you will see very commonly seen menus right here. This over here is basically the table of contents, your map data or GIS data. You have layers and your map drawing. You also have various tools that you can move around and customize. Your ArcCatalog window, which is something that started with ArcGIS 10, is over here on the right hand side. Now there is an ArcCatalog an ArcCatalog program that's separate, but again, what's nice is you can actually see some of your data in folders in this ArcCatalog window. This is considered your data frame where you see your data, but if you want to go look at your map, then you want to toggle onto this. So you're just going to get some I can't say that word. You're going to get used to the ArcMap interface with the first lab. Some things that are important with ArcMap. ArcMap documents are there to view data, analyze data, and map the data. They can store symbology, which are basically visual properties. They store your page layouts and other map features, but they only reference the files. The data in the map do not reside within the map document. There are only links to the files in this map document. So the extension for a map document for ArcMap is MXD. If you move an MXD around, you have to move the data with it, or next time you open up ArcMap, you won't see the data. So it's not like Photoshop or Adobe Illustrator where all of your graphics are stored in one document. This is, we are not drawing features. We are displaying features using symbology and data that reside in different locations. So with Chapter 2, we're going to talk a lot more about how to organize GIS data so that you don't have problems with mapping the data and analyzing the data at a later time. Thank you and see you next time.